Morning, everyone. I think we'll just kick off. People will find us where they find us. We're not going to wait for anyone. I hope you're all having a good day today. And today we'll be looking at SciPy and Matplotlib. This will mark the last session. There's supposed to be 9. We're supposed to also cover pandas. But once you have NumPy, SciPy, and Matplotlib, you have everything you need to work with pandas. The only difference is that in pandas, they introduce a new type called a data frame. The data frame is essentially a table, just like what you'd have in Excel. So I'm going to leave that to you. Hopefully, what you have garnered from this course or this sequence of courses is this central idea of types, operations, and constructs, and how those form the foundation of everything you need to do. For you to understand a programming language, you need to have this repertoire of working with types, operations, and constructs. The types are the things themselves, and we've talked about this several times, many times. Types are essentially how you, I'm sharing my screen. Let me just move this. Types are essentially how you get things represented on the computer. And then operations are what are those types capable of? And you use the operations from those types to actually effect the kind of algorithm. So we are not going to cover any algorithms in this course, but algorithms are an essential now next step for you to make progress. And then the constructs are things that come with the language. The language is designed with the constructs to express certain kinds of ideas. So, for example, if you want to do some looping, you use a certain kind of construct. If you want to do branching, use a certain kind of construct. If you want to have contexts, closed contexts, that's what you use. You can use a with construct in Python. I'm going to leave those for you. I can assure you that the fundamental ideas, let me actually just write here on the screen so that I really want to cement this idea. And you need to, if you ever get stuck, this really is how you're going to get out of trouble. So let me just get this. I want to write in yellow because we have. So there are 3 things we've talked about: types, um, types, and operations. Every type has its set of operations. And then the constructs are now the linguistical things that you work with. And I created a video on YouTube, so you can actually check out. There's a video where I walk through how you actually solve any problem. So you always ask yourself, what is the type? And for that, you use the type function. The type function will tell you what the type is. If you're ever stuck, the type function tells you what the type is. And then once you know what the type is, you need to go to the documentation to find out what the operations are. So operations are the next step. And for this, you have to go to the documentation. And for Python, the documentation is very simply, and you need to memorize this docs.python.org/library. So this needs to be on your fingertips. If you're ever stuck and you need to figure out what's the right operation to use, you go to the documentation, docs.python.org. If you're using another library like NumPy or SciPy, you go to their documentation. If you're using pandas, you go to their documentation. If you're using Django, you go to their documentation. Always go to the documentation. Why? You need to master the documentation. The documentation is how you find your way around. It's like you have a house and you want to walk around this house. How do you find out what is in that house? You have to go through the rooms. You will find out that one room has a particular view, another room has a particular ambience, another room has got, maybe tiles which on the floor, which mean that it's easy to clean. All these different properties of the different rooms. And that's why you need the documentation. The documentation is like the house for that language. So you need to spend time on that documentation. You should always have a tab open to that documentation. And then the last thing is now the constructs. You need to master the constructs. The constructs have very particular structures. And initially, I brought your attention to just three very powerful constructs: the if construct, the for construct, and the def construct. But in the next class, we looked at the class construct, how we can build classes. We may have also covered the while construct in some of the problem sets, but there are many, many constructs that you can then use. And these constructs are sort of the linguistic building blocks. If you look at a language like Scratch, I don't know if anyone has come across Scratch. Can I get by a show of hands how many people are familiar or have seen a language called Scratch? Scratch, who has seen Scratch? Has anyone seen Scratch? Okay, we have one person who has seen Scratch. The rest of you never seen Scratch? Okay, second person who's seen Scratch. Well, Scratch is a programming language. It's usually used for teaching kids. Let me show you on the, I have to stop this. Scratch with MIT. I think it is, okay. It's created by MIT. So it's a programming language that is built using building blocks. And let me just see if I can share a short video. You really need to explore what is available technically. Don't confine yourselves just to your learning material. Explore, watch YouTube videos, find out what crazy. Oh, so this is a good example of how you build applications in Scratch. So this is a Wikipedia page. And when you look at Scratch, let me open this in a new tab so that you can actually see it with a lot of detail. Where is that? Open. Okay, so it has opened here. Or here. So this is what they're like Lego. If you know these toy blocks that children play with for little construction sets, and with Scratch, what they do is they give you these blocks, and right here in the middle, this is where you write your code. You write your code by putting the blocks together. You see they have a little bump which sticks in with a little notch on every other block. And that's how you then align them, and you modify the parameters of the properties of each of the blocks. So constructs are the blocks. If you can see here, they have, each of these are constructs: glide, point in direction, but there they use it for animations, and kids can actually make video games, not video games using Scratch. But they're essentially the building blocks, and that's what these constructs are. Constructs are your building blocks. If you want your code to go through a certain loop, you've probably seen flowcharts which have got decision blocks, and they have got input blocks, and they have routine blocks, and they have a start. And for example, this will then maybe go back here or something like that. And then there's an end. Each of these blocks actually, they can very neatly map to constructs. Okay, so these are the three things. Now, whenever you're solving any problems, always ask yourself, what is the type that I'm working with? And once you know the type, you can then find the operations. And you keep on doing this. You can loop between these two parts ad infinitum, as long as you want. And then occasionally, when you need to do something special, you need to make a decision, you need to carry out a loop, you need to remove a block and have it as a function, then you ask yourself, what's the right construct? And even within that, you then go back all the way now to this part where you then find what are the types I need in building my function and so on, or in building my construct. So these are the three key ideas. Something I really want to highlight about operations is when it comes to operations, there are two classes of operations. And I really want to emphasize this now. There are operations that are associated with a type, okay? And let's look at that in the documentation. So if we go to the Python documentation, I want to point this out from the landing page here for the library. So if you look at this page, now the thing about Python is it comes loaded with lots and lots of libraries which do special purpose things, okay, for data types, for numerics, for functional programming, for file directory access, data persistence. All of these are sort of like little toolkits that allow you to do very specific things. However, 2 points I want to make. Number one, you can accomplish, and I can tell you quite confidently, you can accomplish 99. Let me change the color. I just want this to really, really stand out. You can accomplish 99% of all programming. Int, bool, float, string, none type. I'll just call it the none type. What am I missing here? Maybe complex. Okay, that is sort of exotic for engineers. And then we add on the list and the dictionary, okay? And these three, so these items here and these ones here, you can write 99% of code just using those. I want that to sink in for a minute. You can accomplish 99, you can practically, without even using the class construct, without even using the while construct or the what's it called, the with construct, the match construct, all those, you can accomplish 99% of code. In other words, what we have gone through is enough for you to master 99%. That's point number one. Point number two is, even without all these libraries, without all of these libraries here, all these different things that are provided, the two things that you need are basically, let me highlight this, the built-in functions, which we'll look at in a second, and the built-in types. Just these two alone are enough for you to cover 99% of anything you need to do. In other words, you can spend a whole year just mastering these two sections, and they will help you. You can write practically anything. Okay? It means you can work with Django, you can work with SciPy, you can work with NumPy, you can work with Matplotlib, just using only what is available in these two. Okay? So the operations, so these are the types. Okay? These are the types, and each type has its own operations. However, there's the other class of operations that are important for you to pay attention to are these built-in functions here. So let's just look at that right now. We'll go into and look at that. So there's just a handful. There are not many. It's only these ones here. We've already looked at a number of them. So you've probably seen the len function. When we looked at container types, you had to use the len function. You have all looked at the input function. You have looked at the bool, how to do coercion. You have looked at the int function, okay? You have looked at the print function. What else? You have definitely looked at the type function, which is what we said right here. This is what you need for you to find out what type there is. You have probably played around with the max function, the min function. If you worked with the containers, there's a float function. What else? Let's see. These are also all covered. They're covered in your book. Also in the book, also the enumerate function. We've looked at range. It's also available in quick wins. If you want to make something a string, there is a string function. I think we may have covered some, but I'll exclude that for now. There's also sorted in the book. What else? Complex. And so these are sort of the building blocks which are of operations that are not tied to a particular type. Of course, they will work on certain types, but they are not locked to a type. These are general purpose operations that are available. For example, the list, it works on any sequence type. If it's a string, a list, a dictionary, a set, a frozen set, a tuple, a byte array, a bytes, all those, len will work on them, okay? Oh, yes, and of course we list. How could I forget? List and dict. Where is dict? Here is dict for creating dictionaries. But this is what I really want to emphasize. You need to master these. Spend time with these functions. Learn about them. Have these open. Read through them. Play around with them. you will really sharpen your understanding. Okay? So these are the class of operations. Like we've said, a lot of operations are tied to a type, but we also want to be aware that there are operations that are completely typeless. They are not bound to any particular type. And those are the ones you also need to master. You need to master how to work with them. Okay? So those are the real emphases. As we come to a close of this course, I want to leave you with these ideas. Watch this part of the video multiple times because these are the fundamentals. Even before you go to algorithms, algorithms are now assume that you're familiar with a language and you now want to express particular problems, okay? Whether it is searching through strings or sorting strings and so on. Those are important fundamental algorithms to understand, greedy algorithms, dynamic algorithms, recursive algorithms, and so on. But these are the fundamentals. For you to have familiarity with the language and use it everywhere, you need to have these fundamentals. I'm going to pause here before we now turn our attention to SciPy, and we'll dig into SciPy and look at what SciPy provides. But I want to stop here. Are there any questions? This is our last session, and I want to know if you have any questions. If you have any questions, ask them now, because I won't be available as we have been for the last few weeks. Any questions? Okay, going once, going twice, going, going, gone. Okay, fine, great. So let's turn our attention today to SciPy. So I'm going to clean this out, and then we'll move on to SciPy. So last time what we did is we looked at NumPy, and we said that NumPy is fundamental. Like, it is a fundamental library. If you're going to work as a numerical engineer, whether it's you go into data, you go into AI, and I'll tell you something, you all have the foundational knowledge for that, the kind of stuff that's working in AI. Because as engineers, you are trained, you've got a lot of mathematics background. So if I were you, I would invest all my effort into mastering the mathematics you're learning right now. If you can, get a tutor, a private tutor. If you can hire someone to give you extra classes in mathematics. I know that sounds strange, but I can assure you that mathematics is the one thing that is almost impossible to find once you leave university. So right now, when you're an undergraduate, if you can hire a tutor, either one of your lecturers or a student who's gone ahead, or someone who's doing a master's and needs some pocket money and they know the mathematics that you need, invest heavily in mathematics. Mathematics is really, really a superpower. Right now, I think you're learning differential equations. You may be doing partial differential equations, but you're doing a lot of linear algebra, right? Is that correct? Can I get a sign here? Can you type in the maths topics you covered in the last year? Please put them in the chat. What topics did you cover in your last year? Okay, I think I'll have to call names so that I can get some responses because nobody's responding. Um, Mike Stanley, could you please type in what you remember? One topic that you remember from your maths for the last academic year. The same thing, Binaiza, Jordan K, Jordan, not Kisera, Jordan K. And can I have Umulkier? Each of you, please type in a topic from the last academic year of mathematics. Okay, calculus, okay. Which calculus? Integration, different. Okay, very good, Jordan. Thank you very much. Integration, differential equations, probability. You did linear regression. Okay, good. What else? Thank you, Mike Stanley. Let's just give him a like for that. And Jordan as well. Omolo, differentiation, mean value theorem, antiderivative. Excellent. Thank you very much. Anyone else? Eugene, Charlotte, Nasra. Can you please type in topics from the maths that you covered that have not been added before? Oh my, am I making people drop off? Polar coordinates. Excellent. Thank you, Beniza. Eugene, waiting for you, Charlotte. Patience. Antiderivative. Okay, thank you, Jonathan. Can we type in something that has not been typed before? But let's appreciate those other responses. Thank you very much. Thank you, Jonathan. Maximum and minimum values. Okay, is that for a function? Probability and statistics. Okay. Thank you very much. Sets, complex numbers, very good. Yes. Okay. So let's appreciate everyone who's given a response. Give them a thumbs up, please. Okay, so as we said with NumPy, NumPy is fundamental. Can we type into the chat, what is the fundamental type in NumPy? What is the fundamental type in NumPy? What is the fundamental type? N-dimensional array. Okay, can you give it to me? Thank you, Eugene. Thank you very much. Can you give it to me as, according to the documentation, what is the name of that type? Excellent, Eugene. Excellent. Top marks. 100 marks for you. Excellent. And it's an ND array. Very specifically, it is, well, yes, it is the ND array. Excellent. Top marks. Now, so that is the type. And then the library, the NumPy library, is full of functions. Full of functions for working on ND arrays. So we saw that there are all manner of functions. I won't cover that again. Now, SciPy builds upon NumPy, okay? So if you go to the SciPy documentation, so what I have here, I'm going to zoom in just to make sure it's big enough for everyone. Once you go to the SciPy documentation, this is about algorithms, okay? So if you're lazy, you don't want to write your own algorithms, then this is a good choice of algorithms to use. Now, NumPy does have algorithms, but all those algorithms are usually tied to the ND array. We want to do different things with an ND array, but we are not topic specific or domain specific when it comes to the kind of algorithms we're applying. And SciPy now builds upon NumPy by now introducing scientific algorithms that for scientific computing. Scientific computing is a very broad field, but it entails every discipline which is usually data rich and requires the processing of data through very specific algorithms. Now, here's a secret for you. Okay. Now, I know a lot of you, you've not engaged very deeply, but I want to awaken you to this idea. If you want to get a job in data science, these are the libraries for you. So data science, whenever you see the word scientific computing, that's essentially what data science is. So you need to master these libraries. These are the libraries that will be your bread and butter. And every other library that builds upon NumPy and SciPy, like scikit-learn, like PyTorch, like TensorFlow, they are built upon NumPy and SciPy. So these are fundamental. And as you progress through your engineering education, I would encourage you to try and apply some of what you learn in class through these libraries. I don't know if have you covered DFT, the Fourier transform, and the discrete versions of the Fourier transform? Can I get a thumbs up if that sounds like something you've met before? Do you know what a Fourier transform is, or you don't know what a Fourier transform is? Okay, that's fine. Okay. But in your third year, you will be introduced to the Fourier transform. The Fourier transform is the mother of all transforms. Okay, and it's an important mathematical tool that can take one domain of a function and translate it to another domain. So, for example, if you have let's say you have a differential equation which occurs in one domain, you can then make it into an algebraic expression. There are different types of transforms, but they all look the same. You'll notice after some time, you'll begin to notice they have a certain repeating structure. But Fourier transforms are, when you're introduced to Fourier transforms, I would strongly encourage you. Why don't you take what you've learned in class and write a program and see whether what you've calculated using calculus comes out exactly the same using Python programming, using the SciPy library. So SciPy is about fundamental algorithms, which are about scientific computing, which is just another name for data science. Whether you go into climate science, whether you go into AI and machine learning, whether you go into genomics and bioinformatics, whether you go into fields like, which are the other data heavy fields, like astronomy, or if you work in quantum physics, you have the foundations. What you're learning as an electrical engineer is essential for you to go into nanotechnology, virtually any field. That's why I say invest in your mathematics. If you want to go far, you have to invest deep. So this is a library that you will use. You will use it all the way to PhD and beyond, if that's what you want. Or if you go into professional industry, then you'll still use this library. Even in quantitative finance, a lot of the functions that you use, you can find them within SciPy and NumPy. Okay, so let's start by installing NumPy. So we're going to do an installation, which is just the same. So I'd like someone to type in the chat, how do we install SciPy? Same pattern as with NumPy. Can someone put in the chat, how do we install SciPy? Anyone have any clue? Using the Python terminal, you type numpy dash dash pip. Okay, thank you for trying that. That's a good attempt. I'd like you to try it out and see if it works. Yeah, it would be good for you to try it out and see if it works. Can someone try and see if that works? And if it doesn't work, what error do you get? Thank you for trying, Jordan. Pip install SciPy. Thank you, Florence. Well done. Well done. Yes, that is definitely one way to do it, and that will work. Okay. If you are on PyCharm like I have here, you can open the Python packages. I don't know what to call it. This little window here at the bottom of this little toolkit, and you can use it to install. So these are what I have installed, and you can search for SciPy. Okay, if you search for SciPy, you'll find it right at the top there, and you can then click install, and it does exactly the same as what you have typed there. I don't know if they have a console. They probably don't make it visible. Just one second. Let me see if there's a console. No, they don't have a console. Let's just see. Install from disk on VCS, manage repositories. So they don't expose how it's actually doing the installation. But you then click install, and it does exactly what you said. So this is actually running your console, and you think you can open it, but it prints whatever you see on this tiny window here is exactly what you get when you run pip install. However, I want to introduce you to something new, okay? I want to introduce you to something called UV. So if you come to the install page of SciPy and you look at the installation instructions, so you can ignore all that at the top, there are several ways of going about it. There's a project-based way of going about it, and that's what we look at. And as Florence has said, there is the environment way of doing about it. Now, while we are here on the subject of environment, if you have been paying attention, pip creates for you a private Python for that particular folder or particular project. So it just creates a private Python for you, and everything you install is only available locally. So for example, in my example here, we have a .vn folder, and that .vn is actually where the Python is installed. And if you look inside the bin folder, let me just pull this apart, you'll see you have these different, you have Python here. And I think it's just a short link, which is back to the source Python, but it creates a private Python that you can then install libraries. So what you see here, lib here, is all the packages that we've installed. So for example, we've just installed SciPy, and SciPy will be put right there. So all the libraries, everything is put inside this folder, like that. Okay. The next thing, so this is pip. Pip will create for you that private Python. Something else that you need to be aware of, and I think is very useful to learn, is something called Conda. Now, the Conda project is a way to create virtual environments, but which are not confined to Python. So you can have all manner of applications within it, and it's private. It's a very nice, clean way of making an application self-dependent. I won't go into the details of that. But today what we look at UV. Now, UV it's actually written in Rust. It's a programming language called Rust. It's a systems language, very low-level language. And when you use, the beautiful thing about UV is it is extremely fast. It is so fast, like it's crazily fast. Like let's just look at so extremely fast. Like it's so fast, it's crazy. And this is good because it saves you a lot of time. So if you look at this image here, it shows you how fast it is. It takes like 0.0 seconds compared to all these other equivalent tools. Poetry takes about a second. PDM takes, so there are very many different Python project managing tools, but it is unbelievably fast. So what I want us to do is to use, if you use UV then allows you to work with SciPy, but within a project. So, but you need to install UV first. Now, we won't install UV. I just wanted to bring your attention to this. There are many tools available that you can use. But now that hopefully you have installed, so I'm going to give you 2 minutes to install SciPy, and let me know if you have any errors. So please install SciPy using either pip install or using, don't use Conda, just use pip install, but I want you to be aware of UV as a tool that you can use in the future. That's what they highlight here. So 1 minute, 2 minutes, we'll be back at 38. Okay, can we all click on the tick on the text message I put into the chat to indicate that you have installed SciPy? So should we end the class here? I'm happy to end the class here if nobody is nobody's installing and working through the exercises. Do we need more time? Are we on our phones? I need an indication that I am communicating. Okay, I'll give you 2 more minutes. Thank you, Moyeku. 2 more minutes. We'll resume at 42, 43. Let's call it 43. Okay, so I see 19 people have installed. Thank you. I think that we needed to kickstart a few things. Now, let's bring our attention to the library. So we've talked about what this library is, but let's see in detail what this library has before we start playing with this library. So it's a collection of mathematical algorithms. So at the heart of it, it's all about mathematics, which is then applied in scientific applications, which is built on NumPy, as we said. Now, within this library, there are a number of different packages or sub packages. They call them sub packages. And each of these packages is very well documented. It's really remarkable. They walk you through tutorials and exposés of what you can do with the library, which is separate from the API reference. The API reference exposes all the functions within a particular sub package. But the user guide here walks you through several examples that you can apply. So there are cluster algorithms. Now, cluster algorithms are usually used whenever you have a lot of data and you want to try and structure the data in various ways. Let's see if we can look at just a snippet of what's available within the, they don't provide a link to that. That's strange. Cluster. I don't know why they haven't. It's strange. So they do have one for linear algebra and FFT and interpolation, but they don't have one for, I'm a bit disappointed, cluster algorithms. Okay, those are very specific. We will focus on the ones that they have provided. So let's just make a few notes as we go along. Okay, so please pay attention to this. As I said, a really powerful way to strengthen what you understand in class is to try and express some of the things you learn in class using code. And these libraries make it very easy. So as we talk about cluster algorithms, I don't know why they don't provide a link. There are a lot of physics and mathematics constants. I think we can find them in the API reference. So let's just look at the API reference. AS.cluster, there we go. So the cluster algorithm has got things like k-means clustering. K-means clustering is used whenever you have, imagine if you had a set of points, like you on some two-dimensional grid, you had points which were randomly scattered together, and you want to cluster them and find the groupings, the natural groupings. K-means clustering is a way to do that. It's a very simple idea. It essentially will try and calculate a mean for every cluster, and then it will, for every grouping, and then assemble clusters based on the distance from that mean. So that's what the clustering package does. And they've provided nice algorithm for you to do that, and it's quite straightforward. There is also hierarchical clustering, which you can use, but we won't go into details. Constants is something you'll probably use a lot in engineering. So they have all manner of constants, for example, the speed of light. I think they have two parameters for that, just to make it explicit. C is what you use in mathematics, but the speed of light, again, is just explicit. Magnetic constant, you've probably done this in physics, mu naught. This is in free space. Epsilon naught, this is for vacuum permittivity constant, which is for electric constant. The Planck constant is provided, and they provide two values, one in a literal value. H bar, which is Planck constants reduced. And there are so many others. Avogadro's number, Boltzmann's constant, Stefan Boltzmann constant, electron mass, and so on and so forth. These are all provided out of the box. You never need to, Google or enter them in your program. They are provided directly within the library. Okay, let's just see. There are very many constants, quite a number of them. I think these ones at the bottom are provided using a dictionary. So to access these ones, you will use the literal text here with a dictionary. So for example, if you wanted to get the value for a particular constant, you're going to use the name as provided here, like alpha particle mass. That's what you'll enter here as a string, and it will return a tuple of the value, the unit, and the uncertainty. Uncertainty is essentially to what extent is this value estimated. So it gives you a measure of the uncertainty. Some values have an uncertainty, some don't. Okay, so that's constants. Data sets. I've never used the data sets library, but you can play around with that. If you're doing differential calculus, you can use the differentiate. It can give you the derivative of a function. If you want to get the Jacobian, you'll see this in third year. The Jacobian of a function is if you have a multi-valued function, you can get a matrix of all the derivatives. So the Jacobian, it's just, I don't know. You can reference this on what's it called on Wikipedia. So if you have some function which is of x and y, and then you can get the Jacobian, which is a matrix of all the partial derivatives, die f, die x1, y1, die y1, and so on. So you can fill that in with all the partial derivatives. Actually, it's for a vector valued function, I think. But anyway, Jacobian is one way of doing it. Then the Hessian is the second derivative of, again, a multi-valued function. And these are things that are useful when you come to your third year and you're dealing with multi-valued functions. So you'll come to that later. FFT is a particular algorithm for calculating the Fourier transform. It's called the fast Fourier transform because it's very efficient, and there's a very particular algorithm for that. Okay, so there are very many forms. There is the fast Fourier transform, and then there is the inverse Fourier transform. These are in one dimension, and then there's a two-dimension version, and then there's an n-dimensional Fourier transform. All of these are discrete Fourier transforms. In other words, you are calculating the Fourier transform, but you are using numerical estimates as opposed to with an actual analytical form. Okay. So anyway, the point you need to know is that you have the Fourier transform here. There is I think this is a legacy pack, so you don't use this one. You can then do integral calculus with that, with this particular function. So it's called quad, which is from the traditional name of quadrature. And you can get quadrature of a vector valued function or the adaptive cubature of, so this is now different. Cubature, double quad, triple quad, n quad, if you have multiple variables, and so on and so forth. All these functions are here. Essentially, what I'm trying to say is everything you can do mathematically, you can find within SciPy. Then there's interpolation functions. If your interpolation is when you're trying to estimate a value which is within a range of values that you have. So if you know x at this point, you know x at this point, and you know the value of x and y there, what are the values in between? That's what interpolation is. There are some IO functions, not really interesting. Today we'll spend some time looking at the linear algebra functions. And then SciPy also provides, so if you're solving systems of linear equations, you'd use the linear algebra function. There is n-dimensional image. So if you have images, you can use the functions that are here: convolution, Gaussian filter, and so on, minimum filter, maximum filter, Laplace filter, Prewitt filter, Sobel filter, and so on. They're all available for free directly, okay? ODR is for orthogonal distance regression. I've never used this, but you can read up on that. Optimization functions. If you have a function and you want to find the optimal value that meets some objective function, these are all available here. Signal processing. There are a lot of signal processing functions, convolution, FFT convolution, and so on and so forth. Filtering. I think when you get to fourth year, you look at filters. All those filters are here. In fact, let me just see. There's a Hilbert filter, and so on and so forth. And then you have, if you're dealing with sparse data sets, sparse arrays, these are arrays where big arrays, but with only a fraction of the values within the array are populated, then you'd use this. And then there are spatial transformations. Oh yes, if you're working with three-dimensional data, and then there are some special functions like the airy functions, elliptical functions, Bessel functions. So you have a lot of things in here. This is very rich. I just wanted you to see an overview of what's available, what you're getting for free, open source, completely. I'll pause here and I'm going to ask, do we have any questions? Anything that you're curious about? Okay, no questions. So let's proceed and we shall delve into the linear algebra library. So what I'd like you to do is to open your Python console. So we'll open the Python console like what I have here. And if you have installed SciPy, then you should be able to check that you have SciPy. If you import SciPy, then you should get no error. It means SciPy is available. So the linear algebra library is used for, it's used for matrices and vectors and operations. It's essentially, it's the algebra of vectors and matrices. Okay. Now, the SciPy library is built on top of three actually. Actually, there are two, LAPACK and BLAS. You can Google this later. These are libraries which are written in, I think, C or Fortran or both. Um, and they are extremely efficient, very fast linear algebra capabilities. So SciPy just provides a front end to using these libraries. Now, if you noticed, NumPy also has a linear algebra library, and depending on how you install that, it will be provided using those two libraries, BLAS or LAPACK. But with SciPy, they are automatically available. So it's compiled with BLAS and LAPACK support. So if you ever want to work efficiently, go for the SciPy version of the linear algebra library. So let's start off with some simple problems here. So we looked at last time, the last thing we looked at was some matrix multiplication. And that was the last exercise that you were doing. And if you recall, you can actually multiply them. I think we have I don't know if the multiplication is here. So this is a scalar multiplication here. And this is a matrix multiplication of multiplying one matrix with another. So why don't we start off with this? Let's walk through this example here. So we'll also import NumPy, and we'll make a matrix. A is numpy.array, and we're making at 1, 2, 3, 4. So that's A. Okay, so I need to import NumPy as NP, and then I run that again. So A is that, and if you look at A is our array, okay, just like what we have here. We can do an inversion. If we install, so let's import SciPy dot import the linear algebra library, so linalg. So this is one way to import it, so that everything will be available on the linalg namespace. In other words, we'll need to reference. Oh, sorry, that's wrong. Sorry, from SciPy import linalg. So now everything will be available on the linalg namespace. Now we can inspect that namespace by using the dir linalg and see what's available on that namespace. So we have all these, this is the module, but all these are the functions. You can actually inspect them and see what's available. The underscore, leading underscore, means that don't use this. This is used internally. Don't rely on this implementation. Let's just see the ones which are not with an underscore. We'll begin to see the methods. So Koleski, show, solve, banded. These are all the functions that are available on the linalg namespace for you to use. Okay. So maybe what I should do is I should open that page on the API reference. I go to the API reference and I go to the linalg library, and we'll see that exactly what we've seen before. These are all available here. Okay. Eigenvalue problems, decompositions, matrix functions, okay, matrix equation solvers, and so on. Okay, let's keep going. So now we are going to invert. We shall use the invert linalg. We are going to invert that that matrix, which was A. Okay, we'll get the inverse of that. So this is the inverse. How do we know it's the inverse? Because if we multiply this using that matrix, let's try this out and see if that works. Someone is writing on my screen. Let's see if this works. It may work, it may not work. So it actually does work. So that is our matrix operation from last week. And you can notice it gives us the values here, 1 approximately, 0 precisely. This is approximately 0 because it's to minus 16, 1 times 10 to minus 16, and that's 1, which is the same as an identity matrix. So in other words, when you multiply a matrix and its inverse, you're supposed to get the identity matrix. That's actually what the definition right here at the bottom, finding the inverse. The definition is that A times B is equal to the identity matrix, which is exactly what we've seen here. So here we're using the lin-alg and we're using A from NumPy, and you see they work very interchangeably. I think they assigned a vector. So let's just do that here. So B is equals to np.array, and we have a vector 5, 6. 5, 6. Okay, so this is, so b.shape, it's a 1 by 2. So it is a horizontal vector. And so what we can do with that, so now that's what it is. We get the transpose of B to make it a vertical vector, and that will make it vertical, 5.6. We can get the shape of that. Now that's going to be different. It's 2 by 1. So 2 values times 1. And now we can multiply. If you multiply using times, that will be an element by element product. So if you said A times B, so this is a element by element product. B had got the values 5, 6, and A had got the values 1, 2, 3, 4. So if you multiply 5, 6 by 1, 2, 3, 4, it will multiply the top by 5, 6. It will multiply the bottom by 5, 6, which is why I end up with 15, 24, 5, 12. But if you want to do a linear algebra operation, you'd have to use a matrix multiplication, which is A dot B transpose, because they have to have the right dimensions to multiply each other. So that's now different, and the result will be a 2 by 1. If you multiply a 2 by 2 by a 2 by 1, you get a 2 by 1, which is what we have here. You can actually check the shape directly. So that's just to get us started. I think it may be possible to multiply them. Let's see if we can actually do this. If we use, so this might fail, A times B dot, and we do get the same result. So the at operator is also used for that. Okay, so that's enough for that. It would be, okay, so we get that. Okay, now let's look at some basic proper routines. So this is a matrix A, or an ND array, which is 1, 3, and that. And we want to, if you actually want to calculate it, the inverse, you have to get the determinant, 1 over the determinant times the matrix of cofactors. If you recall this, you probably covered this not too long ago, and that's what it gives you. So we're just going to test this again. So let's set A is, so I'll give you as an exercise. Can you run that code that is there at the bottom there? If you have that, let me give you the page, the link to the page. Run that example and make sure that you get the same result. Get your hands dirty. So let me give you 5 minutes to run through that example of finding the inverse of a matrix. Is anyone having any trouble? If you do, please pop it in the chat so that we can learn from your mistakes or the challenges that you're facing. Let's not waste any challenges. Let's exploit these challenges and make the most and learn from them. Now, please don't copy and paste anything. Type everything out to build muscle memory. Can you please tick whether you've completed that task? Anyone completed the task? Where are we struggling? Are we typing slowly? Or are there any errors? I need to know where you are. Please type in the chat. For the A dot, I'm getting different values for the last column from those on the screen. Great. Could you please share your screen? I'd love to see what you're experiencing. Let's learn from your challenge, Omolo. Oh, thank you. You're sharing your screen. Thank you very much. Let's give a big thumbs up to Omolo. Okay, so could you please just expand this part here? Just move it up. If you put your mouse on the red line, you'll see it will change into a size handle. You just push that up. Yes, very good. Yes, excellent. Okay, so could you scroll to the beginning of the example? So A is equals to 135,251,238, and then you get the inverse, ln of inverse, and you get minus 1.48, 0.36, 0.88, minus 0.36, 0.04, 0.08, 0, minus 0.12, 0.56, and 0.16. Okay, so this far, everything is okay. So A dot linalg in A, we want to double check. We want to see if we get the same. Okay, so your question is, why are the values here? Is that what you mean? Why are the values different? Can I can I please get an indication of the specific question? You could unmic yourself and just speak. Omolo, please help us with an indication of what the problem is. Is it the values here are different from what are on the screen? Okay, that's a great question. Very good question. And it's very illustrative of the challenges of scientific computing. Now, in the 5th year, you're going to do a course called numerical analysis, numerical methods. But you might as well be aware of what numerical methods are. Whenever you, okay, in mathematics, for example, you had some function, let's say you want f of x is the integral of some function, okay? So some f of, we call it u du, okay? And we are going from, let's say, some limit a to limit b. This is all you're all familiar with this. So this is a definite integral, and we end up with a function f, right? Now, what are the implications whenever you are dealing with integrals? Well, if you recall, in the definitions of an integral, you use things like limits. So, for example, we say the limit when let's say u goes from 0 to infinity. Okay. Now, the fact that we have infinity means there's already a disconnect between what's working on your how it is in real life in the actual equation and on your computer. So on your computer, you cannot simulate infinity. There will always be some precision problems. And that's where numerical methods come in. So numerical methods are the ways in which we can carry out estimations for actual functions in such a way that we can be faithful in our calculations, but also take into account that the computer has got finite precision. Okay, so even when you're solving things like a floating point numbers, floating point calculations, like if you get the square root, and you'll see this maybe if you look at, I don't have an example off the top of my head here, but the fact that the computer uses a discrete approximation, we will always end up with rounding of errors. And those rounding of errors depend on the way your CPU is configured. So you probably came across 32-bit computers, 64-bit computers. I'm not sure if there are maybe 128-bit computers. I'm not sure about that. But anyway, 64-bit is sort of the standard. But depending on how your operating system works with the hardware that it works with, then the way the precision is calculated will then vary uh, markedly. Oh, what is this? Okay, so you shared us an image. Let's just see what that is. Give me 1 second while it loads. So let me just share this with everyone. So an import, what is this? A traceback. Okay, sorry, it's not clear to me what that is. But anyway, the whole point about this is when I run the estimation on my computer, when I run it on your computer, depending on what operating system, what how our OS is configured, how our hardware is configured, we will get different values. But, and this is a key point, because of the size of these values, these are practically zero. These are practically zero. They are so small that they're practically zero. So that it turns out if you were to rewrite this such that you are replacing the values, those tiny values with zero, it will end up like 1, and you have a 0, and then you have a 0, and then you have another 0, you have a 1, and you have a 0 again, and you have a 0 there, you have another 0 there, and you have another 1. And this is an identity matrix. So I'll call this I3. This is an identity matrix in in 3 dimensions. So that's why we have the values you will get will be different. Okay, I think they will mention that somewhere. I don't know if they do. Great question. And you see, I hope you understand the value of asking questions. Questions expose new opportunities to learn. Can I encourage you? Please, please, please ask questions. You need to learn to ask questions. It's your survival skill. If you don't ask questions, you don't learn. So thank you, Omolo, for being brave enough to share your screen and giving us an opportunity to all learn this principle or these ideas. So now you're aware about numerical methods. So when you're going to your 5th year, you will approach the 5th year with much more awareness, and there may be tools that you can use to understand and apply what you're learning. Okay. Great. Thank you for sharing. Now you can close your screen. Let's move to the second one because we are running low on time, and I also want to get to plotting of graphs later on. So solving a linear system. So here we have essentially the same numbers. If you pay attention, you'll notice that this linear system here, let me get my pen. This linear system here has got the same values. The coefficients of x, y, and z are 1, 3, 5, 2, 5, 1, 2, 3, and 8. Exactly like what we have here. So in other words, we can jump straight into the next question. The only thing we need to do is augment our matrix with the solutions, with the values on the right-hand side. So let's do that. Okay, so if I scroll down, so now we're going to solve it. We could solve it using the inverse. So we use exactly the same. We could invert both sides. And we'll end up with, now we have a vector here, x, y, z, and we are getting the solution, which is going to be the inverse of 135 times the solution of that set of system of equations, 10, 8, that. And our answer is minus 9.28, 5.16, and 0.76. But how would we actually do it? Well, in this case, what do they do? Do they augment it? So minus b, solve 4, 5. Okay, so unfortunately, they are not showing how to solve, but we can solve it. So let's actually solve it and try and get the same result. So the only thing is we'll need that vector on the side, and we'll apply what we know. So we'll make our solution vector b is equals to, and we give the values there, 10, 8. So it's a NumPy array, so np.array, and we want it to be, so it's going to be the values 10, 8, and 3, okay? So there we have b, okay? Now we know that this is a row vector, so we'll need to multiply it by the inverse. We already have the inverse, so we already have a is equal to, we've calculated the inverse, so let me just do this quickly. A is equals to np.array, and we give it the values. We have 135, 251, 238. Okay, so there we are. And then we'll get the inverse of that. We use linalg dot inverse of A, and we get whatever we got there. So now we are multiplying that inverse, and we have, so that's the inverse, which we get right here. And we can multiply that inverse by that vector, but we have to convert the vector B into a column vector. So we can actually just even use the matrix operation A at B dot T, the transpose of that. No, that's not correct. So A inverse, and it's multiplied from the left by B. Improper mismatch codimension. Okay, then. We should use solve. So we'll say A dot. I wanted to use the at operator, but let's just use dot. And we will. Okay. No, that is checking the solution. So we are here, we are solving NB linalg dot solve. And we have A and B. So this might fail depending on how we should specify a B. So we have to specify the transpose of B, and that gives us the answer that we have right at the top there. So all we need to solve is the right form of, we need a column vector, which is where we transposed our row vector into a column vector, and we provide it with the matrix A. It will internally do the inversion and so forth, and we end up with exactly the same, minus 9.28, 5.16, and 0.76. Do you have any questions on that? But this is just a taster. As I said, there's so much more you can do with this. But I just want to make sure that we are in line with what you have been taught so far. Now, we've seen the determinant here when we are calculating the inverse. We need 1 over the determinant times the matrix of cofactors. So the matrix of cofactors, which gives us this big ugly thing here. But if you wanted to get the determinant on its own, the equation of the determinant is given by this here. Now, this looks really complicated, but essentially the determinant is you're adding up for each of the columns. You'll have positive, negative, positive, and then you'll add those values depending on how you combine them. So that's why you end up with, so for that whole thing here, these are the matrix of cofactors. We have 1. Let me just illustrate this clearly on the screen. So here we have 1, which is taken from this value here. The matrix of cofactors is this matrix here, 5, 1, and we're getting actually the determinant of whatever is inside there, right? So 5 times 8 minus 1 times 3. It's just a pattern, and you keep repeating it. And this expression here captures that idea. So 5, 1, and then usually it's just plus, minus, plus, and then it is minus 3. And for 3, the matrix of cofactors is this 2 and 2 here, and this 1 and 8 here, which is what we have here, 2 and 2 and 1 and 8. And then plus 5, and the matrix of cofactors is this 2, 5, 2, 5, 2, 3, 2, 5, 2, 3. And when you add that, you end up with minus 125. But if you wanted to get the determinant directly, what would we do? So we still have A, and we can simply get the determinant of A. So A dot, I think it is linalg dot det of A, and it just gives you that, it's that value minus 120, minus 25, okay? Now, the other thing you can do in linear algebra is you can compute norms. Norms are a way to sort of reduce a matrix to a number. And there are many types of norms. We won't go into the details of that. There are many types of norms that you can use and you can define. So for example, there's something called the Frobenius norm. Let's just look at that in the documentation, and we see how how these are defined. So I'm going to clear the screen. Let's just say norms. So there is a whole set of norms here. Let's see, where are they? The basics. There's a norm function. So let's drill down into that. So A is a matrix or vector. And then ord is an argument which defines the order of the norm. Is it an integer? Also, it could be an integer, a positive infinity minus infinity. Fro is, we'll read this in the notes. And then nuke is something else. Choose the axis. We saw this when we looked at NumPy. Keep dimensions. This is either set to true or false, and check whether it is finite, which is either true or false, and it's optional. So let's look at the values of ORD. The following norms can be calculated. So if you don't specify anything by default, it will calculate a Frobenius norm, which is what it says here. So none will be a Frobenius norm, or if you specify Frobenius, Fro. A nuclear norm, and all of these other options here, okay? Now, there's an equation for the Frobenius norm. Essentially, you get the absolute value, you square it, and then you get the square root, which is like what you'd get with Pythagoras. Okay, so that's just an example of working with norms. I won't go into the details of that. Someone mentioned that you've done least squares. I think you have done least squares as part of linear regression. When you're doing linear regression, you need to solve problems using least squares. And these are provided for you directly from the, so here's the Jacobian actually. The strategy is to minimize that, which is, I think, the Jacobian. And the functions that are provided are rather straightforward. You'll go through the documentation on this. So this has just been a quick introduction for you to see SciPy, what you can do with SciPy. I don't want to go into a lot of mathematical examples, but I want you to be aware of what is available, how you can use it, how the documentation looks like. If you've noticed, it is essentially the same as for NumPy, because it's authored by the same people. So there are many, many examples. General inverse, which applies even when you have complex numbers. Decompositions, there are different ways. So eigenvalues and eigenvectors, you can calculate that using, so eigenvalues essentially are, the values for lambda which satisfy this equation. And then eigenvectors are the vectors that allow this equation to be true. So I'm going to stop there for SciPy because I want to shift gears. I want us to look at how to do plotting using the Matplotlib library. So I'm going to pause here. Are there any questions on SciPy before we depart from SciPy? No, no questions. Okay, that's fine. So now do you want a 5-minute break? You want a 5-minute break? Okay, then let's have a 5-minute break. And then in the last piece, we'll very quickly zip through these plotting, and then I have an announcement to make. So 5 minutes, we'll be back at 33. Okay, let's proceed. Okie dokie. So now let's turn our attention to plotting in Python. So we've looked at NumPy, which is a fundamental type library. Now we've looked at SciPy, we've done an exploration, played around with some of the functions available in linear algebra. We haven't really gone far in that, but we've just touched on a few things. But occasionally, or quite often, you will need to convert data into visualizations. And that's what the what's it called? Just one second. That's what the Matplotlib library is used for. So let's switch gears now and let's look at plotting with Matplotlib. I'm going to share my screen in just 1 second. Okay, good. There we go. Done. Okay, so let's look at Matplotlib. And we're going to be very practical about this. So as before, installing Matplotlib should be straightforward to you now. So I would encourage you to actually go to the terminal and try and see what happens when you run pip install. Oh, wow. If you run pip install, you can list, first of all, and see what's available. So do I have Matplotlib installed? I do have it installed. So I think I have the latest version. I already have NumPy and I have SciPy here at the bottom. So install Matplotlib. I'll give you just 30 seconds to run that. Oh, great question. Is SciPy dependent on NumPy? Can it be used independently? It is dependent. And that's what we saw in the documentation. If you recall, right here at the top, if you go to the user guide, I don't know, where is it? Yes. It says here, it says SciPy is a collection of mathematical algorithms and convenience functions built on NumPy. So SciPy is built on NumPy. But if you install SciPy, because it's a separate library, some of the functionality you get will be optimized, more optimized than you would get with NumPy. So it's always good to have both. Okay, great question. Great question. Great question. So here we are. We have, please install Matplotlib, and then we'll move on. So I'll go straight into plotting. So now we'll be back into our familiar environment. We'll be using PyCharm as before. So we're going to start off. Why don't we do this? Why don't we create a module called plotting? So I'll create a new module, a Python file called plotting. So now I have this new module, and we want it to have the standard structure as before, and we'll have a function for each type of plotting, okay? And we'll just call those functions. The first thing we need to do is we could install globally matplotlib, not install, call it. So we say import matplotlib plotlib.pyplot. It's a bit of a strange one. .plot pl as plot. So we're giving it a name alias, and we want NumPy also available for us. So NumPy as NP. Okay, we also have an alias for that. And we'll create a function to plot lines. So plot lines. And within that, we're going to do everything we need to. So plot lines. And now what we're going to do is we will start by using the function linspace. If you recall last time, we had linspace. So np.linspace. And we want a linear space from 0 to 2 times np.py. Remember, NumPy also has some numerical constants, and we want to get 200 values. And we then will calculate, so x, we can print out what x is. Let's just build this as we go. we'll print the value of x using an f string just to reinforce what we've done before. So here we have our plot lines function. And if we run that, then it will actually show us we have 200 values of x. X is an array. It goes from 0 all the way to 6.28, which is double 3.14, which is pi. And we have 200 values. We can check for that later on. Now we're going to use some of the efficient functions. We are not going to use a for loop. We shall just directly get a new value y, and we shall get the value of the sine of x. So the sine of x is not just calculating the value on one value of the x, sine of x. It's for the full array of x. And then we can further print that. And if we run that, we now have two arrays. We have x and y, and now we can plot them. So now I want you to, this is the pattern. We will use plot. There's a function called subplots, okay? And we'll just use it as it is. This is one of the unfortunate things about Matplotlib, that it has functions which just don't make sense. So ax is equal to, they'll make sense later on, but for now they are sort of nonsensical. Subplots, okay? So it gives us two things, a figure object and an axis object, okay? So fig and ax are actually two distinct objects. We can actually check the type of what these are, f, and we can see what the type of that is, and we can see, let's actually do the type of fig, and we shall get the type of ax, okay? And it will tell us what these are. Ax equals, and if we run that, so now we see that fig is an object of class matplotlib.figure, so that's the figure, and ax is an object of the class axis with this annoying underscore here, and axis, so it's an axis object. But now let's actually do the plotting. So we plot on the ax object, ax.plot, and we'll plot x and y. I hope this shows up. So that what that does is it does the actual plotting, but it doesn't make the plot visible. So we'll do plot.show to make this visible. Okay, and we don't need to return anything. Okay, I'll clean that up, and I now run that, and I see a lovely plot that shows up on my screen here. So can I give you 2 minutes to run that? Well, what I can do is I can push this code and then you can pull, for those who have gone this far. So I'll push this code. We haven't even added this. So let's add plot. Where is plotting? Oh, wow. Where is it's inside here? Oh, what a shame. I'll move it here. It's in the wrong place. Okay. So now it's here plotting, and we shall add it to Git. Counting characters. I don't know. I'll just add this to Git also. And then I'll commit and push. Drawing an ellipse, plotting. So if you want, you can pull the code from the repository. It may cause some conflict. So when you pull with rebase. Make sure you pull with rebase. So there we go. We have managed to plot the sinusoid over 2 pi. Now you can actually change the values here. If you want it to be, pi over 2, pi, or pi over 4, pi over 2, 3 pi over 2 over 4, and then pi, and so on and so forth. But we'll look at modifying the axis later. So that's a simple example of plotting lines. Now let's try something else here. Okay then, let's try something else. Now we are going to graduate from plotting to plot a scatter plot. So we shall, let's go back to our plotting class here, our module. So that is what it is about plotting lines. Now let's do a scatter plot and see how that looks different. So these are just formulas that you learn how to use. There's not much to understand here. These are just routines that you develop over time and you master with time. And you just use them over and over again, okay? So let's plot scatter. And again, we have NumPy. Now we are using random. I want to import everything at the top. So we'll generate some random numbers. So we'll use random. And in the interest of time, I'll just copy and paste these. here, no, let me just type them. Let me just type them so that we can see they go. So we're going to generate a list of random. So this is something called a list comprehension. You're going to come across this later on. We will generate some random numbers for underscore in range of 30. So this is a list comprehension. You will see this cropping up again and again. And y is random dot random for underscore in range. So we have two sets of random numbers. So what do we expect? We expect a cloud of points. Again, we do this fig.subplots, and we are going to scatter. So x.scatter is the name of the function, x by y. And then we do plot.show. And we need to call this function. So I'm going to hide this here, and I'm going to call this plot.scatter. So if I run that, now I should have a second plot somewhere. Oh, plot.scatter. Why don't I have the scatter plot showing? Let's just run that again. Plot.scatter. Okay, x.scatter. Why am I not getting? Okay, maybe I should rerun it. What's going on here? There we go. I don't know why. That is strange. Ah, I get it. Okay, I get it. I get it. So this is our scatter plot. Very simple scatter. Okay. Now the next thing, we'll skip that exercise. I'll put this in the class anyway. Let's plot a histogram. Now, a histogram is usually from a vector of values, and we want to bin them so that we can see what the distribution is. So let's look at how to do that. So define plot.the histogram, and we have random again. So now our data is equals to random. Now we're doing some modification on this. Random dot, we are drawing from a Gaussian distribution, 0, 1, for underscore in range. There are more efficient ways to do this. So we're doing 1,000 values. So this is essentially a normal distribution with a mean of 0 and a standard deviation of 1. And again, we do fig, arcs, subplots, and then now this is how it does it. It gives us the bins, the patches. You'll see this all in the documentation. Actually, let me take you to the Matplotlib. Matplotlib. And then we zoom in. You may notice again, they look very similar to one another because they're all developed by the same group of people. So there are many things here. There's a getting started, there are examples, there's references, and there's a documentation. And they have somewhere, one of the things I love the most about this library is that they have a gallery. I don't know where the gallery is. It's not here. There is a gallery here. So this gallery is full of every possible type of plot you can think of. Strange plots, ugly plots, beautiful plots. Like you can see this one here has got smileys. So this is so rich. They show you how to draw plots where you have a scatter plot, but with histograms on the sides. All manner of plots. This is probably the most valuable thing in Matplotlib. Contour plots, strange plots. These are like contour hatching. All manner of plots are available. You can put images onto your graph. You can draw contours with points, overlaid with points. And all of these are possible. Subplots, axes, figures, text. You can even change the projections. You probably see this in third year when you do board plots. No, not board plots. Smith and Wesson charts. Sorry, Smith and Wesson. Oh my goodness, that's a gun. There's a there's a plot that is a circular plot when you're Smith charts, and maybe called Smith charts. I don't know why I call it Smith and Wesson charts. Box plots for statistics. So this is probably the most valuable thing that you can ever use. It's just got everything: pie charts, polar charts, and all these things about text and labels. So this is probably the most important resource. Like if you want to do any kind of plot, you'll always find someone has done it before. Changing the colors, changing the shapes. They are all available here. Very, very rich. And then of course you have the user guide and the API reference. So matplotlib.org is the name of the library. Okay, let's just go back and quickly walk through this. We have only 9 minutes before I have to leave. So here, args.hist data, and we want 20, and we specify what the density is. Density, show us the density also. Okay, and then we do plot.show. If you're beginning to notice that there is a pattern here. So I have to run this again. Okay, I haven't called it. So I'm going to hide this one. Let me push this scatter and hist. So that's been pushed up for you. So now I can do plot histogram. And let's see what that looks like. So that's what a histogram looks like. It didn't show the density. I thought it would show the density, the line estimate of that. So this is a normal distribution. If you run this multiple times, you'll notice that they keep changing because we're getting random values and it keeps changing. Yeah. Okay. And then I will leave the box plot for you. So box plot, you just use a function called box plot. And again, plot.show fig arc subplots. That's straightforward. Let's do some interesting things now. Let's do a multi-plot, multiple plots on the same. And but then this time we are going to save it to a file, okay? A PNG file. So that's an interesting thing. So let's do def plot multi-plots and export. So everything as before. So we'll take the same, here we have what? We have multiple plots. So let's take the data from the scatter plot here. I just paste that there. And let's take the data from the histogram. So now we shall have a graph that has both the scatter plot and the histogram. Now, how do we do this? We shall say fig arcs, and now this is where we see the value of subplots. Subplots, we specify how many plots do we have. And we specify them like the way you'd specify the rows and the columns of a matrix. So we want one row with 2 columns. Okay, so we say 1 by 2. They really try to be consistent. That's what I really like about them. So here we have A0. The A0, A is actually now a sequence of axes, and we can reference them independently. So A0 is the first plot, and A1 will be, so let's not use scatter, we'll use the scatter here. And AX1 is the histogram. So we shall, we shall do the histogram and the data, okay? And then we shall do plot.show just to see it first of all. So let's run that. Oh, we have to call plot multiplot. So let's hide this. And we say plot multiplot. So if we run this now, we have 2 graphs. We have one on the left and one on the right. Okay. Now let's do something interesting. Let's save it to a file. So now this is where fig comes in handy. So plot.show shows the plot, but fig is where we can actually save the fig, and we'll save it as plot.png. And then we can say plot.close. And this is useful if you're running, we'll close the figure. Suppose you're running things on you are running some code, it's called headless. You're running it in a way that you don't want to see the results. The results are all stored in a folder and you can check on them later on. This is how you do it. You do it headless. So if we run this now, we will still plot and show, but now when we check inside our folder, we have our file plot.png, which we can then display on a web page or do whatever we want. Now, occasionally we want to have a legend on our graph. So let me just make these changes. I commit and push. So multiplot. I will commit and push. So let's come back here to our plotting module. Now, suppose we want to add a legend. A legend, you'll use a legend whenever you have multiple plots on the same graph. So let's see that. So plot legend. And it's always very instructive to do this. So here we have, so X, I just now copy and paste because I only have 4 minutes. And then I'll walk through them and explain what they are. So we have X using linspace as before. We have the sine, and then we are also adding Z. Z will be the cosine of X. Now we expect to see that there will be 90, I think it's 90 degrees out of phase from one another. So here is fig. We do the subplots. Again, we are only drawing one plot, okay? And let me just make this wider. I just minimize this one so that I can get space. And so I'll say plot the first one, and again, I will say on the same axis, I will plot the second one. And we say show us the legend and show. So what I need to do here is I now need to add my plot legend. And if I plot that, we now see our legend, which comes on the bottom left. There are a lot of parameters you can use to control where it is positioned, the colors and everything, the text. You can even change the text there. You can write equations and so on and so forth. Okay, so now we have plotted the legend. We can see what that looks like. What if we wanted to add a title to our plot? Well, you can have set the axes and the labels of X and Y. So I'll just make these changes to this one. So everything is done again on the axis. So if we run that again, this time we have a label for X and we have a label for Y and we have a title for the plot. Okay, and then finally, and the last one is we can change the axis. You can change what's on it. So you can add a grid, change the tick marks, set the limits, add lines and so forth. Let's see what this do. We're just adding complexity on top of this. If we run that again now, oh, look at that. We've changed the ranges. Okay, now we have text in red. We have a grid line, and we've even reversed the orientation of the numbers. So just fooling around. This is just illustrative for you to know what's going on. So that's it. I'm just going to commit. So grids, text, legend, and so forth, ticks. And I'll push that for you. That's up. So in the last 2 minutes, I'm going to give you a chance for any questions before I make an announcement. So great question, Muyeko. What window is this that shows the plot? I can only see the terminal output that the process finished with exit 0. Oh, this is on PyCharm. So PyCharm is smart enough to run your program and capture the visualization. If you run them directly, that's a good question, very good question. Very great question, actually. If I go to the terminal, I go straight into the terminal. Let's clear this. And I list the contents of my directory. You'll see I have my plotting file there. I can call it Python plotting, and now it will do things differently. It'll actually open a window, a separate window here. What it was doing with PyCharm is it just intercepted that window. And this window is nice because you can actually use it for zooming in. So you can zoom in to see that certain part. You see, we can go in very close. Like if you want to get the solutions of an equation, you can do all that using this window. Okay? Great. Now, if there are any other questions? So this is our last class. If you have any questions, please post them also in the Google Classroom. I'll send an assignment for today for I'll set the deadline, and then I'll also mark the work of those who finished and submitted, and then I'll hand over the marks to your lecturer, Mr. Ondeng. But before we go, one last announcement. I'm looking for interns. I'm looking for bright young people who want to expand their technical skill. So if you are interested in going further with Python, if you are interested in working on interesting problems, I run a 4-month unpaid. I want to be very clear. There will be no pay for this, but my hope is you will learn a lot. So if you're interested in working on challenging and interesting projects while developing your Python skills, email me at info@sci2pro.com. And for those who are interested, I will send you a couple of challenges as part of the selection process. And so send me an email saying you're interested so that I can get your email, and then we can kick it off from there. Do not, if you're not interested, please, this is not mandatory. It is just for those who are really keen and want to go to the next level and work on problems. So with that, I say thank you and best of luck, best wishes. And I will give you the problems to work on for the exercises, and take care and bye.